All right, we are continuing on here, chapter 13, and we're doing some equilibrium. So I think last time, I vaguely remember what we were doing. I think we talked about how to, again, manipulate equations and how they affect, again, the K value. So a couple of reminders of that. Again, if you have an equation here and you have a K value and you need to say reverse the reaction. The effect on the K value is it will actually again be 1 over the K value as basically your products become your reactants become your products. So basically your K just kind of flips around. Again, if you need to multiply by a common number, say you need to multiply the equation by 3, what we would do to the K value is actually take the K value to the third power. So if you need to multiply by a common number, you take basically that K value to whatever number you multiplied as kind of like the exponent. And obviously as well, if you need to divide by a common number. So again, if we kind of took this guy and divided this whole thing by 3, that would return us back to our original sort of equation. And in this case, we would actually take the cube root there of the K value. And again, if you had to divide by 2, you take the square root and so forth. So those are very common ways that we sort of manipulate equations. A reminder as well that if we do add some equations together, what we do with the K values is we actually multiply the K values. Again, we don't add the K values. So that's also something a little bit different than sort of like the Hess's law sort of thing. So very commonly people get confused or mix those sort of processes up. So like when they reverse a reaction, they'll change the sign of K, or if they multiply it by a number, they'll multiply K. So again, it's not the same as what you do with delta H. You got to, again, adjust K correctly. And again, we do multiply the K values when it's all said and done. We got into at the very end there, really the main calculation of the season here, which are ice tables. And ice tables stand for initial change in equilibrium. And they're really the calculation that we use to determine equilibrium concentrations, also can be equilibrium pressures. Again, typically molarity we go into these tables with, or again, if you're doing pressures, it should be atmospheres is usually what should go into there. And we have an equation, say like this here. And we would have, say, our initial sort of concentrations. And if you're not given anything in terms of our product side, as we talked about last time, it is safe to sort of assume usually that it's 0 to start with there. This also helps us sort of understand which way this reaction should go. If you're just given reactants, really the only choice is the forward direction in this reaction. And because of that, what we would expect to happen is our reactants should start to decrease with time. Our products should start to increase with time. And that's represented in the ice table with minuses and pluses. And the change is usually represented with the letter X, and X is usually what we use for the change part. So in this case, this would be something like minus 2x minus X, and this would be plus 3x. Once again, when we do this, it's really important to take the coefficients into account because that is what gives you the proper mole-to-mole relationship. It does essentially the stoichiometry part of the calculation for you when you do that. So you want to always make sure that you include that. This stuff just gets brought down to our equilibrium line. And usually at this point, what we would do is this would go into our K expression for my really badly made up one here, but we'll do this here. And obviously you would probably maybe be given a K value or something like that. And what we typically would do is kind of go into the equation with everything on the equilibrium line. We would solve for X. And again, that would then allow us to figure out what all these X values are and actually get some equilibrium concentrations. Now to solve for x, one way that we talked about last time, and I think we did like a little sample problem I made up, I think, we could use the quadratic formula, which is very common in these sort of problems. And that is a formula of like ax squared plus bx plus c equals 0, where a, b, and c here are what goes into the quadratic formula, where x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. And as we saw in that example, and as we talked about, you do end up usually with 2x values in this particular case. And when you do a quadratic and you get 2x values, you do have pretty much all the options in terms of your x values. You can have 2 positive x values. You could have a positive and a negative x values, and you even can, believe it or not, have a negative 2 negative values when you get there as well. So what will happen is one of those values, not necessarily the value itself, but one of those values, when you go put it back into the equilibrium line here, will yield you a negative number. And that is no good because, again, you cannot have a negative concentration, you can't have a negative pressure or anything like that. So that's how you would know that this is not perhaps the right one to choose in that particular case. Any questions on that stuff we talked about the last time? All right, so I think we laid up right about here. So let's go through this real example, unlike the one I made up last time, and talk about how we go about doing this. So we have at 1280 degrees, the equilibrium constant for this reaction is 7. If the initial concentration of Br2 is 0.663 molar, we want to know what is the equilibrium concentrations of everybody. So this is a classic sort of ice situation table. And we could write our equilibrium expression, which is our products, which in this case is Br, and we do need to square it because of the coefficient, divided by the concentration of Br2. And again, that's going to equal lucky number 7. We'll see how lucky it is in a second. And this, again, is, as I mentioned before, probably not a bad choice in this class. If you're not sure what to do, try to think maybe like an ice table is a pretty good choice in a lot of the calculations that we do. So we need our equation here. And we're going to initially put what we got, which is 0.663 of this guy. Once again, we are not given any information about our product, so we can, again, safely assume that it's going to start out with 0 in this particular case. That then gets us to the change part, and as I just mentioned before, because there's really no products, we only have reactants, pretty much we are going to be forced into a forward direction for this reaction to take place. That means my minuses should be on the reactant side, which I would say 98% of the time they usually are. And this will be minus x. Again, the coefficient here is 1, so it's basically 1x. Here we would be increasing our product, so this would be plus 2x. Once again, the 2 for the coefficient. That's going to, as I mentioned before, take care of the stoichiometry here. We're going to drop this down here and go 0.663 minus x, and this would just be 2x at this point. Any questions on the ice table here? All right, so remember, pretty much the goal here is to solve for x. So we're going to take our equilibrium line and basically put it into our expression here. And if we do that, that's going to basically give me 2x, and that's going to be squared up on top, divided by 0.663 minus x, and that is going to equal 7. So I got a little bit of math here to do. We're going to square the top, which will give me 4x squared. By the way, I'm just going to now move this to the other side by multiplying. So that will then equal what we got here, 7 times 0.663, going to give me 4.641 minus 7x. Remember, we want to get this sort of into our quadratic sort of equation here. So we need to bring everybody to the same side and basically set it equal to 0. As I mentioned last time, it really doesn't matter which way you go. Most people tend to like to leave the x squared as a positive number, but it doesn't really matter. But that's usually what most people like to do. So in that case, I'm going to kind of bring everybody back to this side, and that's going to give me 4x squared. That's now going to be plus 7x as I add that to the other side, minus 4.641, and that's going to equal 0. That is essentially my quadratic sort of equation there, and that's going to be my A, my B, and my C that I need to basically go into my formula there. Any questions on that there? All right, so let's do that perhaps. So a reminder again, x is going to equal minus b plus or minus the square root of b squared minus 4ac divided by 2a. So kind of popping some numbers in here. Do it here. So x is going to equal minus 7 plus or minus. Now, if I do everything in the square root there, I'm going to take b squared, which is 7 squared. If I find out my calculator, there it is. Minus 4 times a, which is 4, times c, which is, again, negative. We do need to keep the negative there, 4.641. And if I do all that inside the square root, you get like 123.256, to which if I take the square root of that, and again, if I can find that button, there it is. We'll end up with 11.10 in this case. That's all going to be divided by 2 times a, which is basically 8 in this case, 2 times 4. That again is going to give us our two numbers here. So we're going to do the plus first. So minus 7 plus 11.10 divided by 8 gives us an x value of 0.513. I'm now going to do the minus part. So negative 7 minus 11.10 divided by 8. Going to give me a negative 2.263 in this particular case. Now, when we look at our two x values here, again, we got a positive and negative, which is very common. We could hopefully see that really this one here is not going to do us very much good, because clearly if I just simply put that number into here, that is going to give me a negative 4 point something. And obviously, again, we cannot have a negative concentration. So that means that this x value should be our winning x value there. And now we're going to use that to go into basically all of our x's in our equilibrium line. So that would mean the concentration of Br2 at equilibrium would equal 0.663 minus our x value, 0.513. And by the way, these are molarity as we're doing concentrations here. So 0.663 minus 0.513, going to give us 0.150 molar. For our concentration of Br at equilibrium, it equals 2 times x, so 2 times 0.13 molar. Going to get us here, we'll call it 1.03 molar in this particular case. And these would be, once again, our equilibrium concentrations of everybody. Any questions on that there? Once again, as we talked about, since this is math, one of the good things, I guess, about it, other than the bad thing of that it's math, I suppose, is we could actually, again, take our equilibrium concentrations we just calculated, which in this case was 1.03, and square it and divide it by 0.150, and you should get 7. And I think you get about 7. Again, may not be perfect, but should be really close with rounding. And I think you get like 7.0 something when you do that. Any questions? And again, I would recommend if you do have the time, maybe pop it back in there just to check, especially if you're doing something like the quadratic. There's a lot of places where you could kind of screw up. So it's a good way to maybe check yourself there at the end. Any questions on any of that there? All right. So let us, why don't you try one now since I did that one? All right, you have a mixture of 0.5 moles of H2, 0.5 moles of I2. We put it in a 1-liter flask. What is the equilibrium concentrations of everybody? And we got a K value of 54.3. All right, so take some time there and calculate it up, see what you come up with. Okay, so let's take a look, see how you're doing. So in this case, we're not given molarity, but we are given moles and liters, which is essentially the same thing. So we might want to calculate our concentrations, which aren't too bad in this case. So we're going to take H2. We're going to take the moles, 0.5 moles over 1 liter will give us our molarity of 0.5 molar for H2. We will also do the same thing for our I2, and it actually comes out the same here, 0.5 moles over 1 liter, 0.5 molar in this case. Our K expression here going to be the concentration of HI. We do again need to square it because of the coefficient, divided by the concentration of H2 and the concentration of I2. And once again, that's going to equal our K value there of 54.3 there. All right, so we could do our ice table. I think I'll flip a page here maybe and do it. Borrow that. That looks good. So initially, we're going to go 0.5, 0.5. And again, initially here, we're going to have 0 for our products as nothing was mentioned. This again tells us this reaction should be heading in this direction since we have no products. Change going to be minus x, and once again here, plus 2x because of the coefficient. And obviously our coefficients here are 1s as well. That means that when we reach equilibrium, 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table here? That again is going to go into the expression we wrote there on the previous slide. So let me pop it back up here so we can take a look here. That equals our 54.3 in this case. So popping our numbers in there, that's going to give us 2x squared divided by 0.5 minus x times 0.5 minus x. And once again, that's going to equal 54.3. So again, here we do want to solve for x, and hopefully you saw that you could just put a big square root on both sides. Don't always have to do quadratic, so you can if you like, if you're fond of it, go for it. But you can actually square root both sides here, and that would get you a 2x on top, a 0.5 minus x. The thing I usually forget to do, which is actually take the square root there of 54. So we'll try to remember to do that. 54.3 and a little square root action. Going to give us 7.3689. Again, if you want to do the quadratic, should come out the same, believe it or not. So we're going to multiply this to the other side. That will give us 2x is equal to times 0.5. 3.684, and that's going to be minus 7.3689x. We want to get our x's to the same side, so I'm just going to bring this guy over by adding it really to the other side. That's going to give me 9.3689x equals 3.6844. And one last move here, a little dividing action there, yeah. So we'll divide it by 9.3689 in this case. That's going to give us an x of 0.393. Probably much easier than the quadratic, but again, if you did the quadratic, you actually should end up with the same number there, so up to you. That is the x value. We're going to go into each of these here to get our concentrations. So that means that the equilibrium concentration here of H2 0.5 minus 0.393 molar. That is going to get us there 0.5 minus 0.393. 0.107 molar. We should also get an identical one there for I2. 0.5 minus x 3.93 or 3.393. 0.107. And lastly, for our HI, it is 2 times X, so 2 times 0.393. Gonna get us, it's like 0.786 molar here. And once again, these would be our equilibrium concentrations of everybody. Any questions on that there? Again, if you take these guys and put it back in here, you get about 54, which is pretty good with rounding. And looks like no mistake, hopefully, with that. Any questions on any of those stuff? So again, a good illustration that, sometimes you do have to use quadratic, and that is kind of your only choice, but there are other ways to solve for it. And sometimes it's good to take an easier way if you can, right? Any questions on any of those steps there? All right, let's try another one. Not easy. Test your math skills now that you're warmed up. All right, so we got initial concentrations of H2, I2, and HI, 0.00623, 0.00414, and 0.0224 respectively for H2, I2, and HI. Same equation, same K value. We're looking for everybody's equilibrium concentrations. This might require some math, I would think. I'll try to. I'll grab myself a piece of paper and see how I do. Given the initial concentrations of everybody in this reaction, so we want to basically, before we get into the actual problem, this would actually be another situation where you would want to calculate Q that we talked about last time. Q is that reaction quotient. It helps to determine if a system is at equilibrium, and if it is not at equilibrium, it will also help us understand which way it needs to go to reach equilibrium. Now, we could do that because we are given the initial concentrations of everybody. My guess is it's not at equilibrium, otherwise it wouldn't be much of a problem to do. But more importantly, though, it will help us for sure know for the change part of the table, kind of which way the reaction needs to progress to reach equilibrium. So remember that we do calculate Q the exact same way that we would calculate K. So we would take our HI, and again, we would square it because of the coefficient, divided by our H2 and our I2. So putting in our initial concentrations here, 0.00623 squared. That is definitely not the right number. So I'm going to pop the right number in there and try that again. Good thing they made erasers, I suppose. There we go. So that's actually 0.0224, looks better, divided by 0.00623 and 0.00414. So we calculate Q in this case, and again, we should really do it. This is the second sort of situation, as we talked about with Q, where you should do it if you're given the initial concentrations of everybody, just to verify you're not at equilibrium. And once again, it'll also help us understand which way we need to go. So we got like a 19.5 for our Q. That means when we compare Q to our K value, Q is less than K, which means we're not at equilibrium, which is not a surprise. But more importantly, we know in this case that in order to reach equilibrium, which way does it need to go? Is to go opposite of where that's pointing, towards the product side, right? So again, by doing Q, it assures you that when you do the change part of the table, you're doing your minuses and your pluses in the right sort of direction. This will be like normal, minuses on the reactant side and pluses on the product side. Now, let's just say, for example, I calculated Q in this case, and it actually said that it needed to go to the reactant side. That would mean that we would actually have to do it opposite when we get to the change. These guys would be our minuses, and these guys would be our pluses in this case. So that's why here we would want to sort of calculate Q just to verify which direction this reaction needs to go. And we just verified that it actually does need to go in this direction. Any questions why we calculated Q? Just a reminder as well, why we did not calculate Q in the other examples, there was no possible way to do so. We were not given the initial concentrations of everybody, so there's no way to actually calculate it in the previous couple examples that we did in this case. All right, now that we got that out of the way, let's go do some math, I suppose. Or we could just skip and go to the next problem. Let's see. We got, might be the better choice. I don't know. We'll see. So we got a little bit of this going on here. All right, so obviously here our K expression is going to be the same as we just wrote there for our Q. It's going to be our products over our reactants. And once again, here we're using the same K value we did in the previous problem, 54.3. So popping in our numbers here, initially 0.00623, 0.00414. And also different than some of the problems we did before, we actually do have an initial concentration here of our product, which is 0.0224. So again, a little bit different. We actually do have a value on all of our initial ones. We verify through doing our Q calculation that the reaction is progressing in this direction, which means this would be minus x, and plus 2x. That means at equilibrium here, got a lot going on, 0.00623 minus x, 0.00414 minus x. And this, again, does have an initial, so 0.0224, and this is actually plus 2x. So that is also a common error that sometimes people make. They're kind of used to always doing like minus x's and stuff like that. So it is a plus x on that other side there, like normal. Just like normal, we're going to go into our expression here, giving us 0.0224 plus 2x. That does need to be squared, divided by 0.00623 minus x, 0.00414 minus x. That's all going to equal 54.3. Unfortunately, this is not a perfect square, so a little factoring, foiling, whatever they call it these days, but we need to do a little bit of math. So we're going to roll out here the top. So I'm just going to kind of do them separately, and then we'll put them back together. So for the top, we basically got 0.0224 plus 2x, 0.0224 plus 2x. Again, we're going in and out, right? Sounds good as well. In and out over here. And if we do that for the top, we should get something like this of 0.0005018 plus 0.0448x plus 0.0448x plus 4x squared. Kind of combining everybody together, that gives us for the top 4x squared plus 0.0896x plus 0.005018. So again, this is our top guy, sort of foiled out, if you will. We're going to do the same thing for our bottom here. Do it in a different color, maybe. We'll go blue. So for our bottom, we'll go here, 0.00623 minus x, 0.00414 minus x. Once again, obviously in and out, and then in and out, right? So that is going to give us here, and again, this is the bottom. Going to get here, looks like 0.000258. You obviously can use scientific notation if you wanted to, minus 0.00623x minus 0.00414x, and that's going to be a plus x squared. Again, just kind of combining the terms together, that's going to give me for the bottom x squared minus 0.01037x plus 0.000258. And again, that is our bottom, right? So now we could kind of bring it back together here. So I'm going to then put that guy on the bottom. So it gives me x squared minus 0.01037x plus 0.0000258. That does equal our K value of 54.3. At this point, we need to take what's on the bottom and multiply it to the other side. And if we do that, we will end up with 4x squared plus 0.0896x. This is basically the top that we didn't do anything to, 0.0005018 equals 54.3x squared minus 0.56309x plus 0.001401. Almost there. We're going to bring everybody here to this side, basically. And that finally gets us the equation we're looking for, which is 50.3x squared minus 0.6527x plus 0.00089992 equals 0. That is going to be our A, B, and C here for our quadratic. Any questions on that there? Just a lot of keeping track of. Again, may want to do the top first and the bottom, put it back together. Now putting that into our formula here, our x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. Gonna get us here 0.6527 plus or minus the square root. If you kind of take care of everything inside the square root, 0.2451. And then if you square root it, 0.4951 divided by 100.6. Going to give us our two x values here. If you go plus first, you get an x value of 0.0114. If you go the minus, you get an x value of 0.00157 in this case. In this case, we actually got two positive numbers. So again, we have to kind of determine which one is good or bad based off of really our equilibrium line. So I'm just going to rewrite the equilibrium line of our ice table. And for H2, it was 0.00623 minus X. For our I2, it was 0.00414 minus X. And for our 2HI, it was 0.0224 plus 2x. So just looking at it, this number right here is going to be too big when we put it back in there. That's going to give us a negative number. So that is no good for that one. That means this one looks like a winner. And that means we can now put it into here. So our H2 will equal 0.00623 minus X, 0.00157. And that's going to give us 0.00466 molar. For our I2, putting it into the equilibrium line, 0.00414 minus X. Gonna get us here 0.00257 molar. And lastly, for our HI, gonna get us here 0.0224 plus 2x. Again, remember that is a plus, not a minus. And that's gonna get you there 0.02554 molar. And once again, if you pop those numbers back into our expression, I can't believe it either. You get like a 54-ish, which is pretty good, I guess. Yeah. Any questions on any of those things? By the way, in case you're curious, I did do it myself. Yes, on paper. Any questions on how to do that? So this obviously is a little bit more complicated of a quadratic versus the first one we did. Again, a lot of places where you can run into some trouble. So again, I would highly recommend at the end you maybe pop it back in there and make sure, hopefully, you are close to that K value and check it. Any questions on this one here? All right. By the way, you do need to show work for quadratic, not just punch it into your calculator. Yeah. So you got to show some work and that type of stuff to get credit. All right. Let's take a look at one last one here to finish up for today. If the Kp is 4.31 times 10 to the minus 4, what is the pressures of everybody at equilibrium if you started with 0.862 atmospheres of N2, 0.373 atmospheres of H2? So again, a reminder, as we talked about, you could obviously do an ice table with pressures with the Kp. So works the exact same way, except obviously you're this one here and see what we want to do with it. Besides maybe go to the next one problem as well on this one. So as I mentioned before, it doesn't matter if it's pressures or concentrations. It does work the same. The only thing with pressures, as we've talked about a number of times, is before you go into the ice table, it does definitely need to be in atmospheres to do the ice table calculation. Again, even if they give it to you in some other unit of pressure and they want the answer in some other unit than atmospheres, you do again need to kind of put them into atmospheres and do the calculation. So in this case, our Kp would be the partial pressure squared of NH3 divided by the partial pressure of N2 times the partial pressure cubed of H2. So again, we still need to take our coefficients into account. This is going to equal 4.31 times 10 to the minus 4. So I'm going to flip the page here and do it on here. So just rewrite that real quick. Partial pressure NH3, pressure of N2, partial pressure cubed of H2, and that equals 4.31 times 10 to the minus 4. So initially here for our N2, we got 0.862 for our pressure. We got 0.373 for our pressure. Nothing mentioned about the product. So again, we could assume that it's going to be 0. Change here going to work the same, minus x. Remember, this needs to be minus 3x because of the coefficient. And this is going to be plus 2x also because of the coefficient. That is going to get us here 0.862 minus x, 0.373 minus 3x, and 2x. Just like we've done before, we're going to put this into our expression. That will give us 2x squared divided by 0.862 minus x and 0.373 minus 3x, and that does need to be cubed in this case, and that will equal 4.31 times 10 to the minus 4. Any questions on the ice table or anything up to this point? All right, clearly at this one, this looks scary enough for me as well. So nobody wants to do this. So we need to find perhaps a better way to do this because, this is really not necessarily a math class, right? So in this case, there is a way that we could do this a little bit easier. And the way that we could do it is based off of the K value here. And when we look at the K value, that is a large K value or a small K value? That is a small K value, which means when I reach equilibrium, will I mainly have reactants or products? I would mainly have reactants, right? And if I mainly have reactants because the K value is small, that means the actual change part here is going to be relatively small as well. So we're going to have a small K. We will mainly have reactants. We will have probably a small change. And again, change here is our x. So in this situation, when you have a small k value, you can make an assumption and you could assume that x is equal to 0. Now, you cannot kill all the x's because it's clear you got nothing to solve for. So these are only x's that you would be subtracting from a number or even adding to a number. So those are the x's that we would get rid of. Now, this x we would not get rid of because, frankly, it started at 0. which means anything that gets from 0 is pretty significant, right? If you started with nothing, you have just a little anything, that's a pretty big change, right? So that's why, again, we really don't get rid of that x, besides the fact we would have nothing to solve for at that point. So the x's we're going to get rid of basically is this x and this x. We're going to assume it's equal to 0. This will then make this look something like this, 2x squared divided by 0.862 times 0.373. By the way, we still need to cube that guy. And that's going to equal 4.31 times 10 to the minus 4. This looks perhaps a little bit better in terms of wanting to solve this. Now we could actually solve this. By the way, the thing missed by a lot of people is the top is actually what? Top is 4x squared, not just 2x squared. Yes, so can't tell you how many people forget to square that guy. So make sure you also square that guy as well. On the bottom here, we could get a number. We'll get 0.373 cubed times 0.862. That's going to give us something like 0.044733 equals 4.31 times 10 to the minus 4. We're then going to multiply this to the other side, and that will get us 4.31 to the minus 4 times that. 4x squared is equal to 0.00001928. I'm going to divide first by 4, and then I'm going to square root it, kind of all in one move there. So I'm going to take that number divided by 4, hit equals, and then square root it. And after you square root it, you will get an x value of 0.00220 in this case. First off, any questions on that there? Now, you can make an assumption in this situation, but whenever you do make an assumption, you do have to check it to make sure it's okay to use. So the way that we check our assumption is we're going to use what is commonly referred to as the 5% rule. And the 5% rule is you get your x value like we just did, which was 0.00220. That was our x value. And basically, you take your x value and you divide it by what you were going to subtract it from or what you're going to add it to. And in this case, 0.862 was the number we were going to basically subtract it from, times it by 100%. And if we do that there, you get something like 0.25%, which is a good check, which means this number is good. You could do it for either one. So you could take 0.0020, not 20, there you go. You could actually times it by 3 because that was 3x there, and divide it by our number here, which was 0.373. 373 times it by 100%. And this one also should be fairly good, I believe. And that's usually the case. I would say you got something like 1.77%, also good. You don't usually have to check both. Usually if one's good, usually the other one's good. But as long as it's less than 5%, you could then use that x value. Bad news is if it's more than 5% or 5% or more, then technically you got to go back and solve it some other way. And probably for our purposes, that would be the quadratic. You got to go roll with and solve it that way. So you could also, as we talked about, if you don't want to do the assumption or anything like that, you could still quadratic it and solve it that way if you want. But it can save you some time probably. So since our x value is good, we're ready to kind of get our numbers here. So the pressure of N2 would equal 0.862 minus our x value. And that's going to get us here 0.862 minus 0.00220. Looks like 0.8, I don't know, 60, we'll call it, atmospheres. We got for our pressure of H2, 0.373 minus 3 times X, 0.00220. And that's going to give us 0.37 minus 3 times 0.00220. Going to get us 0.366 atmospheres. And lastly, I'll go maybe right about here for our NH3 pressure. That's going to be 2 times our X, 0.00220. And that's going to get us 0.00220, 0.0044 atmospheres. And once again, if we pop this back into our K expression, we once again should really get our same K value that we saw previously. And I believe you do as well. So 4.6 to the minus 4. So we are good in this case. Any questions on the assumption? Question I have is, why did I not try the assumption on the previous few problems we did? In the previous few problems that we did, the K value was 54.3, 54.3, and 7, right? Those are all considered large values of K, which means you cannot do the assumption on those, because with a large value of K, you would have mainly products, which means you have a fairly significant change that's occurring, so you cannot do it. So you could only try the assumption on really K values with like negative exponents, small values of K. And again, you should always check it, because as we'll go through different chapters, it will sometimes not work, and you will have to kind of go back and solve it through the quadratic. Question on equilibrium calculations. We've done 3 different ways: quadratic, perfect square, and assumption. And these are the 3 ways that you'll be responsible to be able to solve these problems. There is a 4th way that we will not do, but sometimes in books you do see it. It's known as successive approximation. And the idea there is, your X value has to be less than your initial concentration. So basically in something like this, you would put an X value less than this guy for everybody but this guy. And then you would solve for X, and you keep doing that until the number you put in is the same number you get out, which if you're really crappy at it, could be an all-day project. So we will not do successive approximation, but if you see it, sometimes books like to solve some problems that way, but we will not do it here. So quadratic, assumption, perfect square, that is pretty much how we're going to do them. Any questions on any of that there? All right, we'll lay it up there. We're almost done with this chapter. Not too much more to go.